Okay, so let's talk about doing calculations involving the Bohr model. So the Bohr model involves electrons that are orbiting in fixed orbits around a positively charged nucleus, and the simplest is the hydrogen atom, which has one electron orbiting around one proton, and it has the simplest spectrum. So what was observed was these different sets of lines that were emitted in the spectrum of hydrogen, and experimentalists found that the observed wavelengths could be predicted using several different formulae. So for the visible light series, which of course is what was seen first because it could be seen with the naked eye, it's called the Balmer series. They found that if you took 1 over the wavelength, it was equal to r, a constant, the Rydberg constant, times 1 over 2 squared minus 1 over n squared, where n was an integer bigger than 2, so 3, 4, 5, all the way up to infinity, and they could predict accurately the wavelength of the lines. Then they found 2 more series, one in the ultraviolet, where 1 over the wavelength was the Rydberg constant times 1 over 1 squared minus 1 over n squared, where n was a number bigger than 1, and the Paschen series in infrared, where 1 over the wavelength was a Rydberg constant times 1 over 3 squared minus 1 over n squared, where n was bigger than 3. So let's do a few calculations using these equations. So just a reminder of the Balmer, Lyman, and Paschen series. So let's find the shortest wavelength in the Lyman series and the longest wavelength in the Paschen series. Okay, so the Lyman series is 1 over lambda is equal to r times 1 over 1 squared minus 1 over n squared, where n is any integer from 2 to infinity. So I want to find the shortest lambda. So what I want is, obviously, I either want to put in n equals 2 or n equals infinity. Those are going to give me either one of them is going to give me the shortest, one of them is going to give me the longest, which is which. But when I have the smallest lambda, that means that 1 over lambda should be the biggest. So what I want is, I want what value of n is going to give me the biggest value on the right-hand side of the equation. Okay, so I've got 1 over 1 squared minus something. So to make that the biggest, I want to subtract the smallest something from it. And the smallest something will be where n equals infinity. So if n equals infinity, 1 over n squared is equal to 0. Okay, so the shortest wavelength will be where 1 over lambda is equal to r times 1 over 1 squared, which is just 1, of course, minus 1 over infinity squared. So that's just going to be r times 1 minus 0, or r. So my wavelength then is, since 1 over with lambda equals r, the wavelength is going to be 1 over r. So it's going to be 1 over 1.097 times 10 to the 7, which is going to give me 9.116 times 10 to the minus 8 meters. And normally for light we talk about nanometers. That's 91 nanometers. Okay, so that's quite a short wavelength. All right, how about the longest wavelength in the Paschen series? So the Paschen series is 1 over lambda. Draw a line to separate the two. 1 over lambda is r times 1 over 3 squared minus 1 over n squared. Okay, so obviously the two choices for longest and shortest will be n equals 4 or n equals infinity. But we just talked about up above how n equals infinity is going to give us the smallest value of the wavelength. So n equals 4 is going to give us the longest wavelength, because it's going to give us the smallest value that we can possibly get of that thing in the brackets. And so that will give us the longest value for the wavelength. So let's put in our number. So 1 over lambda is r times 1 over 3 squared minus 1 over 4 squared. So that's 1.097 times 10 to the 7 is our R, times 1 over 9 minus 1 over 16, which is 5.33 times 10 to the 5. And remember, that is 1 over the wavelength, so to get the wavelength, we do 1 over 5.33 times 10 to the 5, and we get 1.875 times 10 to the minus 6 meters, and putting that into nanometers, that's 1875 nanometers. Okay, so that's the longest wavelength in the Paschen series. Okay, so going back to Bohr's model, remember Niels Bohr said that the electrons orbit like planets around the sun, and only certain radii of the orbits were allowed. And electrons that move in an orbit and stay in that orbit, they don't emit any light, but if they jump to a lower orbit, they're going to emit light, and if they jump to a higher orbit, they're going to absorb light. And the frequency of the light that they give is given by HF is equal to the energy difference between the two orbits. So E initial minus E final is H, Planck's constant, times the frequency of light. So it's the energy of the photon that's either emitted or absorbed. So if we look at Bohr's model, we can take, remember, for anything moving in a circle, the centripetal force, mv squared over r, is going to be equal to the electric force that's attracting the electron to the nucleus. And remember, for the nucleus has Z, the atomic number, times the number of protons. So the charge for the nucleus is going to be ZE. The charge for the electron is just E. Okay, so the electric force is equal to the centripetal force. If we set those two equal to each other and rearrange it, we get that the allowed radius of the orbit is K, which is 9 times 10 to the 9, remember from the first module, times Z E squared over mv squared. And for hydrogen, Z equals 1, so we just have K E squared over mv squared. Now what Bohr said was that the orbits were quantized so that the angular momentum was an integer multiple of h bar, which is h over 2 pi. So if we take that value for v and substitute it back into our equation for r, and we won't go through all the algebra, what we end up getting is that the radius of the nth allowed orbital is that number n squared divided by the number of protons in the nucleus, Z, times R1, where R1 is a special radius called the Bohr radius, and it's made up of that whole big combination of constants inside the brackets there. Those are all constants. We can put in the values, and we get something that's about half an angstrom, 0.529 times 10 to the minus 10 meters. And so for hydrogen, where Z equals 1, the allowed orbits are just n squared times r1. So for the first orbit, it's just going to be 1 times r1. For the second orbit, it's going to be 2 squared, 4 times r1. And the next one's going to be 9 times r1, and then 16. So we're going to go out in integer squares. We can also calculate then the energy of each orbit by adding the kinetic energy, 1/2 mv squared, and we had an equation for V, and the electrical potential energy for the electron in that orbit. And when we do that, we get Z squared over n squared times another big set of constants there. And that set of constants together, if we calculate the value, it comes out to minus 13.6 electron volts. So the energy of the nth orbital is Z squared over n squared times minus 13.6. So you'll notice that the energies of the orbitals are all going to be negative. The lowest orbital is going to have the most negative energy, and then the higher we go, as we go to n equals infinity, we're going to approach an energy of 0. For hydrogen, remember Z equals 1, and so our equations for the energy are just minus 13.6 divided by n squared. So when we jump from one orbit to another, we go from one value of n to another value of n. And so the energy change is just minus 13.6 eV times 1 over the initial n squared minus 1 over the final n squared. And we can use that to give us the energy of the light that's emitted. And if you look at this equation here, you can see this sort of looks like what we had for Balmer, Paschen, and Lyman, right? So for the Balmer series, we had 1 over 2 squared minus 1 over n squared. So what was happening in the Balmer series is we were jumping down into the n equals 2 orbital, and you can see that in this picture here. The Balmer series of light photons were emitted when things jumped from the n equals 3 or higher orbit down into n equals 2. Similarly, for the Paschen series, we jumped down to n equals 3 and we had smaller energies. And for the Lyman series, which was the highest energy, the ultraviolet, we jumped down into the very lowest orbital, and so we had lots more energy that was emitted, higher energy photons, and so we had a higher frequency and a shorter wavelength. So let's do some calculations using all those equations. I've got them summarized down there at the bottom of the slide. So if an electron goes from the n equals 4 to the n equals 2 orbital of hydrogen, first of all, let's find the energy and the radius for each orbital. So we want to find the radius of the fourth orbital and the energy of the fourth orbital. We want to find the radius of the second orbital and the energy of the second orbital. So you can just use the equation. So Rn is n squared over z. And here we have hydrogen, so z equals 1, so we can just ignore it in the equation. So we've just got n squared times r1, where r1 is the Bohr radius, so r4 is just going to be 4 squared times the Bohr radius, which is down at the bottom of the slide, 0.529 times 10 to the negative 10 meters. And so the radius of that orbit is going to be about 16 times a half, so it should be something like 8. And to be exact, we get 8.5 times 10 to the minus 10 meters, so that's 8.5 angstroms. The energy of the fourth level is just minus 13.6 over n squared. And because it's hydrogen, we don't have any z squared appearing in there. So it's going to be minus 13.6, and our n is 4. So over 4 squared. And so we're going to get minus 0.85 electron volts. Do the similar thing for the radius and the energy of the second orbit, n equals 2. So we're going to get 2 squared times the Bohr radius, which is going to give us just 2.1 times 10 to the minus 10 meters. And the energy is going to be just minus 13.6 over 2 squared, which is going to be negative 3.4 electron volts. Okay, so now we want to calculate the frequency and the wavelength of the photon that's emitted in this transition. So remember, that's going to depend on the energy difference. Remember, HF is equal to E initial minus E final. So we started off in n equals 4, and we're ending up in n equals 2. So our energy difference is going to be E4, negative 0.85, minus E2 minus negative 3.4, and so we're subtracting a negative, so that's going to end up giving us a positive, which is 2.55 electron volts. So that's going to be the energy of the photon, and so I can use Planck's constant to calculate what the frequency is and then calculate the wavelength. So let me go clear some room. So we've got HF is equal to 2.55 eV. So F is 2.55 over H. And I need to put, since my energy is in eV, I need to use the value for Planck's constant that's in eV. So 4.136 times 10 to the minus 15 eV seconds. Alternatively, you could have converted that energy from electron volts to joules and then used the version of Planck's constant 6.626 times 10 to the minus 34 joule seconds. So if I do this, I get 6.165 times 10 to the 14 hertz. And if I want to calculate the wavelength C equals lambda F. So lambda is C over F. Remember, when you do that equation, C is always on top. 3 times 10 to the 8 over 6.165 times 10 to the 14. And I get a wavelength of 4.86 times 10 to the minus 7, or 486 nanometers. Okay, how else could you have calculated it? Well, you could have, if you wanted to, you could have calculated using 1 over lambda equals R times 1 over n final squared minus 1 over n initial squared, and that would have also given you a wavelength of 486 nanometers, and then you could have used that to calculate the frequency. So whichever way makes more sense to you. All right, so what I want you to do is to just do a combination of things like what I just did, and then upload your solution. So we want to figure out what wavelength and frequency of light is emitted when an electron jumps from n equals 7 to n equals 4. And then finally, what's the radius of the n equals 4 orbit? And I just did that, so you should be able to find that out. And then figure out what's the highest and the lowest wavelength in the Balmer series. As you remember, for the Balmer series, you're doing 1 over 2 squared as your first number.